Okay, hi. For this next exercise, you're going to do about AP sequence and also a little bit about geometry, okay? Now, the question is, can we form an AP sequence using the sides of three inscribed polygons, square, triangle, and hexagon, using the same circumference radius? So we have three circumference. They have the same radius. They must be the same, of course. And we're going to draw a polygon inside each circumference. We say that those polygons are inscribed, okay? The circumference, it is circumscribed, going outside, and the polygons, they go inside, they are inscribed. Can we inscribe those polygons? And when we inscribe polygon, it means that the vertex of each polygon must touch the circumference. So can we inscribe those polygons in a way that the side length of each polygon form an AP sequence? Does that happen? Maybe so, maybe not. If it does happen, I want you to tell me what is going to be each polygon side. And if it's not possible, if you say, okay, it's impossible to form an AP sequence building a polygon inside each circumference having the same radius, they are never going to form an AP sequence. If it's impossible, I want to propose a solution so this sequence becomes an AP sequence, because it happens like this. If we have 3 points and they are not linear, we can make, just moving one, we can make them become linear again. Just moving one dot, 1 point, we can make a sequence that it's not linear, it becomes linear. And that is the question, okay? So the first thing we have to go through here is to decide what is going to be the sequence. It's not the sequence, okay? Of course not. I just name it randomly. I want to find out it's going to be what? You can go from the smallest to the biggest, or the biggest to the smallest side, but it gotta have a sequence, okay? And I'm just telling you, it's not this sequence, okay? It's not. Which one has the smallest side? Which one has the biggest side? Think for a moment, okay? What is going to be drawn in here? The first one. Think, and we come back. Assuming you gave your thoughts. If you did not, I'm going to wait 5 more seconds. What I want you to find out is this. The first thing you have to do is you have to put those polygons in order. Which has the smallest sides and which one of them are going to have the biggest sides. Okay? Meanwhile, think yourself. Okay. Assuming you had thought about it, the answer is going to be like this. The more sides we have, okay, imagine this. We have, for a triangle, it's going to be just like this. Okay. Now imagine that we have a decagon. Okay, 10 sides. Imagine we have to put 1, 2, 3, 4, 5, 10. You see, the sides are going to be very small. Okay. So this is the decagon. Now imagine you have an icosahedron. Icosahedron has 20 sides. It's going to be even smaller because we have to put 1, 2, 3, 4, 5, 6, 7, up to 20. So the more sides we have, the smallest those sides get. Okay? So I'm going to start using the triangle as the first one. And they're going to be like this. It's going to be like this. I have to divide in 3, right? It's going to be something like this. Okay? This is going to be our triangle. Now let's go for our square. It's going to be the middle one. This is going to be the square. And the last one is going to be the hexagon. The hexagon you just divide in 3. The 60, right? this 60 degrees, I think so. This like this. Okay, it should be something like this. Something like. Okay, so those are the shapes. And now we have to draw the radius. This is going to be the radius. And this is going to be L1. This is going to be L2 the sides. And L3. This is the radius again. The circumference radius, right? And now our job is to relate. I'm going to pause again. You are going to pause. And you have to tell me the relation between R and L1, R and L2, and R and L3, okay? Now, let's draw the triangle in here, because let's remember some things about triangles. Now, I will try to draw the best I can, okay, the triangle. If this is the base, I don't know, maybe this, okay? Not sure it's going to work, but this is a triangle. Let's draw the first height. Then, yeah, it's not going very well because this should be 9 degrees, okay? It's not, imagine this 9 degrees, okay? Drawing at free hands, it's not very easy. Okay. And what is this point? When all the heights are going to meet. This is the orthocenter. When all the heights they meet, this is going to be the orthocenter. Now, when we make the orthocenter, what is going to happen? If we just make, it's not going to work very much, but okay, I will try to draw in here circumference. So in the end, trust me, okay, the drawing is not the best one possible, but in the end, if we just draw a circumference in here, okay, the center, it is going to be here, okay? If you just draw this circumference, the center, it is going to be the orthocenter, okay? And then just draw the circumference, and that's how we circumscribe a circumference into an equilateral triangle. Well, I just showed you that the orthocenter, it is going to be the center of the circumference that we are going to use. Now, once we know this, let's just make this one a simple drawing. Again, let's make the height in here. This is the orthocenter, and this is very important. Why? Because this is what we want, right? Okay. And if you remember, and this goes for the equilateral triangle, the height of the equilateral triangle, it is L1 square root of 3 divided by 2. This is this height, okay? This is this height, the red one, okay? L square root of 3 divided by 2. And there is a property also, this is all geometry, there is a property that tells us that this portion in here, it is 2/3 of the entire height. So this is the radius, right? This is our radius here. Radius, radius, radius. From the vertex to the orthocenter, it is our radius. This is our radius. And our radius, it is 2/3 of this height, right? Okay? But look, the height it is this, isn't it? L1 square root of 3 divided by 2. Now we have a relation, okay? Now we can write like this. The radius, it is also 2/3 of L1 square root of 3 divided by 2. Cancel, cancel. And now we have a very clear relationship. We know that now radius equals L1 square root of 3 divided by 3. Well, but we don't want to express in terms of radius equals L1. We want L1 equals something, okay? We want to find out L1, so we just have to invert. So what it is important to us in here is this, that L1, it is going to, I just make cross multiplication, 3r square root of 3, okay? But if you remember, it's not nice to live in this form, right? We don't leave square roots at the denominator. What should we do? L1 equals 3r square root of 3, just multiply by square root of 3, okay? You are going to see that they are going to cancel. And in the end, what we want is this. L1, it is r square root of 3. Okay? This is our first relation. All these to get that. Now, let's find out the square. The square is much easier. Okay? Now, let's see. We have, if we just continue in here, we're going to have the diagonal. Okay? But the diagonal from the square is L square root of 2, right? This is diagonal of the square. And this is another r. So the diagonal, it is just 2r. So it's very easy now. So L2, it is 2r divided by square root of 2. Again, multiply by square root of 2, because when we do, we're going to get rid of that square root of 2. And this is going to be 2r square root of 2 divided by 2, okay? Square root of 2 times square root of 2, it's just 2. Now we have our next relation. L2, it is r square root of 2. This is our next relation. And the third one, we have to remember a property, okay, that when you're dealing about hexagons, okay, formed by 6 equilateral triangles. Look here, I'm going to make in red. Everything in here is going to be an equilateral triangle. And why is that? Well, what is the total angle in here? 360. If we divide 360 by 6 triangles, that triangle is going to be 6 degrees, right? Because 60, 60, 60, 60, 60, 60, 360. Well, if this is 60, the triangle has 180 degrees internal angles. And knowing that those two are the same, those two must be 120, right? Because 120 plus 60 is 180. That means that those are also 60. Very easy to prove that they are all equilateral. Well, if they are equilateral, there is nothing else to say that L3 equals R, okay? The R, it's R, R, R. Everything is R or everything is L3. Okay? Now, this is what we have. And now, I'm going to do something like this. Let's save us space in case we need them. Okay, now this is the first part. We have determined the sides of each inscribed polygon. This is the early beginning of the exercise, okay? This exercise is not easy going, okay? We gotta have a patience. Now, if this is supposed to be an AP sequence, all those sides, if those are the terms of our AP sequence, it means that L2 is going to be the average between L1 and L3. Agree? Okay. Now, if that is true, if this is true, I can tell that those three numbers lengths, they are going to be an AP sequence. But they gotta be like this. This is the average of those two. Now, let's just substitute. R square root of 2 is going to be L1 plus L3 divided by 2. Okay, so just make cross multiplication and okay, so first cross multiplication and take this term, go to the first one thing at a time. Okay, now let's put everything to the left side. 2r square root of 2 minus r square root of 3 minus r equals to 0. Let's put r like this in evidence. This is 2 square root of 2. This is a 2, okay? Now minus square root of 3 minus 1 equals 0. And let's do something now. What should we do here? R times this one, it's 0. Now, is this possible to be 0? 2 is square root of 3, 2 minus square root of 3 minus 1. No, this will never be 0. Never. They are all constants, and those constants are not going to go to 0. So this guy must go to 0. Okay, so 0 times something, it goes to 0. And for that to happen, this will only work if r equals 0. Okay? Well, if r equals 0, okay, substitute in here. L1 is going to be 0. L2 is going to be 0. And L3 it is going to be 0. So our sequence is going to be 0, 0, 0. Is this, by excellence, an AP sequence? Well, if you're just looking at those numbers, yes, they are, okay? The first term, 0, second term, 0, third term, 0. What is the common difference? 0, no problems. Okay, this can be an AP. Yes, it can. Okay, it's true. Okay, but what happens is, although this is an arithmetic progression, now, do we have polygons which sides are 0 in length? It's impossible. Okay, so those in here are not polygons. So this is the reasoning that I am expecting you to tell me. Okay, from the math perspective alone, okay, this is possible. For just looking at this part, this is a sequence, it is true, but those are not polygons, so it's impossible. Okay, so the answer for this first part, it's impossible. To form an arithmetic progression with the sides of triangle, square, and hexagon. Okay? Now, we're going to see on the next page, and still this video, what can we propose. Now we're going to the next video, okay? I'm going to make a separate video because the second part can also be seen as a different exercise. So, see you at page 32, next video. See you then.